Now, another thing that is common across everything is the dimensionality reduction part. The curse of dimensions. It's very easy when we look at the data, we come up with all kinds of things, right? If you think about doing the like stock predictions, right? You will, in no time, you will just build all kinds of, features. You'll think of that maybe stocks depend on the gold prices. Maybe stocks depend on the climatic conditions. Maybe stocks depend on the price of the construction industry, price of the cement in the construction industry. Maybe the stocks of stock market is dependent on let's say the people's activity on social media, right? And so on and so forth. In no time, you will have millions of columns, right? When you think about stocks. And each of these, let's say I come up with the idea that, hey, looks like if I aggregate all the newspapers yesterday's news and convert them some way into numbers, I should be able to do the stock predictions. In no time, I'll have like thousands and thousands of columns. And you saw that in case of MNIST, how many columns did we have? The features, yes, 784, right? 28 by 28. That was really, really tiny image. But if you think about like a bigger image that has 1 million columns, right? So in no time, the dimensions of the data start increasing in no time, okay? And this is where a technique like dimensionality reduction comes into play. And this topic is common across deep learning, machine learning, and so on. So you will see that one is the gradient descent, other is the dimensionality reduction, along with the ensemble and hyperparameter and other basic foundation things that we learned. Those are the few things that are common across deep learning and this. Or you can say that deep learning is just one additional additional set of algorithms, like the way we had SVM, linear regression, and decision tree. Similarly, we'll have the neural networks. All right, so let's get started. So some problem sets may have large number of feature sets and making the model extremely slow and making it impossible to solve many number of times, even making it difficult to find the solution. This is referred as curse of dimensionality. So as we studied earlier, that when we saw the feature importances, right, we observed that a lot of features were not important, correct? A lot of features were not important. Here, all these features that we drew earlier, they were not important, the ones that are black. Now, we figured this out after we are done with the training, right? After we were done with the entire heavyweight lifting and so on, we figured this out at the last, correct? And if we could do the training normally, then we wouldn't really need the dimensionality reduction. We need to reduce, we should be able to figure out that these columns, these pixels were not of any use. So we could have actually trimmed our image upfront and probably brought down the total number of features by half, right? Now, how do we do that? This is where we will learn. Also, notice that in case of MNIST, we could actually observe a number of things, right? First is that neighboring pixels are highly correlated, right? Neighboring pixels can be merged into one without losing much of the information, hence further reducing the dimensions of the features. So the dimensionality reduction gives a lot of benefits, such as the model becomes faster, and when you have less number of features, you can visualize, right? The drawbacks, of course, are that you might lose a little bit of information, and we will try to see that how we can minimize the loss. Okay. Now, here's a question for everyone, right? Why I want to ask this question is, I want to emphasize on the fact that all the people who you meet and say that they can see things beyond 3 dimensions, they are probably lying, right? Imagining more than 3 dimensions are hard for people and hard for everyone, okay? And it's just the formulation, mathematical formulation, that gives us that ability to measure and ability to figure out that what does another dimension mean. Now here's a question. Let's just start with a very simple question. What is the probability that when you choose a random point in the unit meter square, right, that point is within its border? And how we are defining the border is by 1 millimeter. So what is the probability that a point that you randomly choose on a cube is within 1 millimeter of the border? Yes? So you'll compute the volume of the border and you'll compute the volume of the cube, and you will divide the volume of the edge by the total volume, correct? Is anybody trying? It comes out to be like this, right? All right. I'll just start with 2 dimensions, okay? Let's say this is our cube and this is the inside of the cube, right? So we are saying that what is the probability that a random point chosen will be somewhere here, right? So this is 1, right? And how much is this? Let's say this is 1 millimeter. This is 1 millimeter, right? So how much is this? This is not definitely 1, but it will be 1 minus 2 millimeters, right? This will be 1 minus 2 millimeters, correct? So the area of the edge is how much? This edge is how much? 1 square, that is the main area, correct? That's the main area, minus what is the inside area? Inside area is going to be 0.998 square. That's right, Gonzalo. This is 1 millimeter, this is 1 millimeter, so you're left with 0.998, right? And when you compute the area of this one, it's going to be 0.998 square, and the outside is going to be 1 square, correct? And it's going to be 1 minus, how much is going to be? Okay, yes. All right, I'll just use my Python. Okay, so how much is it? 1 minus 0.998. Okay, so it's around this much, correct? So which is basically this much. Is that making sense? right? Had this been a cube, it'll be the same thing would become 1 cube, right? 1 cube minus 0.998 cube, right? And you can quickly compute it. This comes out to be 0.006. Yes? So in case of square, point being chosen is basically going to be, if the area of something is bored, you will get the chances of you picking the point in that area is very high, right? So the volume of edge in this case it's going to be 0.006. In this case, it's going to be, the probability is going to be how much? 0.004, correct? This is in case of square, the probability of choosing a point is going to be this divided by 1, right? 1 is in the entire one. And in case of cube, this is going to be for cube. Wow, this is completely illegible. Okay. All right. I'll say it, Arun, Deepak, Gonzalo, Jaya, Jayanarayan, Nikita, Prashant, and Robert and Robin. All right. Is it making sense? Question from Prashant is, how do we get 0.998? So 0.998 is 1 millimeter minus 1 mm here and 1 mm here, right? So 2 mm less than 1 meter. Okay, so the internal dimension, correct? So what do you notice here between this? This is 2D, this is 3D, right? Yeah, 1 millimeter within the border. Border as in this is one border, and we're talking about this 1 millimeter, right? 1 millimeter. So what is it that we're trying to do? We're trying to find the area of the border, in this case of 2 dimension. In case of 3 dimension, we are trying to find the volume of it. And how did we do that? Find the volume of outside, find the volume of inside, and subtract the two, right? And if you can find out like what is the volume of this part, we can find out what is the probability of a dot being in this part. Because the probability is going to be in the same ratio as volumes. Correct? Makes sense? No? Okay, feel free to say, because there would be, it's very high chance that there will be confusion in the communication. Feel free to express, because I'm going to extend this part going ahead. All right. Deepak's point is probability high in case of multidimension because of law of large numbers. Law of large numbers is different. Okay. I'll just describe what it means as we go ahead. All right. Great. So Prashant, did it make sense? Or go ahead in case you have a question. All right, let me probably go back to the question that it makes. So probability of a random point chosen in 1 meter in what is the probability that the point chosen inside a cube or 1 meter square within 1 millimeter from the border? This is basically a square. Okay, so it is this much, right? The area of inside, area of outside. So this is the area of inside a square and area of this. If you subtract the two, you get the area of the edge, area of that, and so on. Yes, you can unmute and ask Prashant if you have. Okay. All right. So we shall move. All right. Okay. So answer is basically just the area of the strip. Okay. And as I was saying that in case, let's say we are given this square, we are asking that what is the probability that a random point chosen in the square is within 1 millimeter of the edge, right? What is the probability? What is that probability? So how will you compute? We all have to find out that what is the probability of it being elsewhere, right? In the whole cube square, like it could be here, it could be here. So what is the total probability, total chances, as well? I mean, and what is the chances that it will be here? So this is basically this. So which is going to be same as the volume of this one or area of this one, divided by the total area, right? Chances of it being here, is volume of this one divided by the entire thing. Volume or area, it's the same. I mean, it's the same thing. So the answer is basically the area of this strip divided by total area. Okay, and total area is 1, and this area is basically subtraction of outside and inside. That's how we can quickly compute. Although we can compute this strip, and compute the summation of these two strips, right? So 1 millimeter into 1 meter, that's 2 millimeter into 2 meters. So, right? And this is 2 millimeter into 2 meters plus, then there is 1 millimeter, which is, say, this is going to be, how much is this from here to here? It's 0.999 and into 1 millimeter. No, 998 actually. 998 and so on. So you will find that it's actually, you can find it this way or the other way. And yes. Okay. So basically the easiest way is to find out the outer one minus inside one, and that's it. All right. So that's about it. So the probability is in the ratio of the area, and the way we can compute the area of the edge is by computing the outside minus its inside. Okay, so that's about it. Yes? All right. Yes, feel free to ask in case Mike, somewhere I was communicating wrong way. Okay. All right. So the chances are in that ratio of the area or the volume. Now, if let's say we had a hypercube, okay, So I talked about two things. One is square. This is a square. This is a cube. Now, if the dimensions grow beyond 3, right, it becomes a cube, or it becomes a hypercube, right? Let's say 1,000 dimension or 10,000 dimensions, right? So instead of squaring cube or doing cube, we'll do to the power 4, right? So in case of square, we basically square to compute the probability, we squared it. In case of cube, we cubed it. In case of maybe a dimension 4D, we will be doing the to the power 4. And if we have 5 dimensions, then we'll be doing to the power 5, and so on. Now, in case this cube has, this hypercube had 10,000 dimensions, if it had 10,000 dimensions, the probability of selecting a point and it is lying in the edge is 1 millimeter. It is lying within the edge is 99%. Okay, so let me rephrase. The way we extended our generalization from 2D to 3D, if we extend the 3D to 4D or 3D to 10,000, the probability of being on the edge or near the edge is very, very high. In case of 10,000, it's like 100% probability that you will be on the edge, right? So what do you understand by this? If you have a hypercube which is having 10,000 dimensions, and you choose any point in this cube, you'll be near the edge always. You will be near 1 millimeter of any of the edges, any of the sides, right? Now, this doesn't make sense, right? So this doesn't make sense because we can't really visualize a hypercube. Reality is that a hypercube is something that we can't really think of how it look. Okay, because we can't visualize that that a hypercube of 10,000 dimensions will be full of edges. It'll be full of edges, right? We can't visualize that, meaning that there is no point in the cube where there is no edge. Okay, so the point I'm trying to make here is that as the dimensions grow, it becomes impossible to visualize it using normal geometry, normal 3 dimensions. Okay, and this is the point I wanted to drive from here. Then second part is that if we pick 2 random points on a unit square, the distance between these 2 points is how much? The distance between the 2 points is somewhere here, like 0.52. You can take a look at how to compute it. Okay. Now, if you pick 2 random points in a, let's say, a 1,000,000 dimension hypercube, the distance between these two shall be roughly this much. Okay, the square root of this much. Okay, and how much is that? Square root of square root of 1,000,000 by 6. Okay, now so there are many things that we can visualize in 2 dimensions or 3 dimensions, because that's what we have seen. But when it comes to many dimensions, we don't really know, we can't really visualize. Like in this case, mathematically, if you pick 2 points in a million dimension cube, the distance between these 2 points will roughly be around this much. Okay. Now, how can that be? Because we have never seen it. We have never seen we have never seen that suddenly it's a unit cube. Okay, it's a unit hypercube and of 1 meter, 1 meter hypercube, and the distance between 2 points in this is 400 meters. 400 meters, though it's a cube. Right? The only way you can think of it is that the diagonal of a cube is more than the side of the cube, right? Diagonal of a cube is how much? Is basically the 1 square plus 2 square plus 3 square. Sorry, 1 square plus 1 square plus 1 square. That is the cube root of 3. No, square root of 3. Okay. No. How much is the diagonal? Diagonal, let's say diagonal of a square is bigger than the sides. Similarly, diagonal of a cube is bigger than the sides, and so on, right? Similarly, diagonal of hypercube is going to be really, really high, really, really big, and so on. So the distance between randomly 2 points is around 500 meters in a unit cube, right? So this is something that sounds really strange. So the point I'm trying to make here is a very important point, that as the dimensions grow, things go haywire. As the dimensions grow, we can't visualize data. As dimensions grow, a number of things that seems obvious are not that obvious. Now, the next important thing I want to express is what is the real curse of the dimensions. That as the columns grow, we require more rows in our data, more instances in our data to give better predictions. All right. So here, like as the columns grow, what happens is that dimensions are growing and the dots are becoming far and far apart. Okay. So say for example, let's say you have 3 dimensions, right? If you need like 3 data points in each dimensions, 3 data points in each dimensions, then let's say you have 3 dimensions and how many data points you will require? You'll require 27 data points in every dimensions. So, to overall 27 data points you will require, so that every dimensions out of these 3 dimensions have equal distribution, like each dimension gets 3 data points. Correct? So let's say you have three dimensions and you want at least three data points in each dimension so that you can plot the line correctly in each dimension, right? For that, you will require, let's say, 3 data points in each side. So overall, how many data points you will require? Okay, you'll require approximately 27, 3 into 3 into 3, right? So higher dimension data sets are at the risk of being very sparse. Most training sets are likely to be very far from each other. As we said here, the 2 data points in a cube are very far. Similarly, in case you have more dimensions, right, the instances are going to be far apart from each other, and therefore more the dimensions, the worst will be your correlation between the two, right? And in case you have like 3 data point here, let me just go back here. Let me try to scribble something. Okay. Let's say in this one, you have 3 data points, one here, other here, and other here, right? Do you fit this kind of line or this kind of line or this kind of line or this kind of line? What do you fit in this, right? Since these data points are far apart, it's very difficult to come up with any of the strategies. Or let's say you are trying to create a decision tree, you split here, 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 or here. How do you split? Because all these values are going to be having equal amount of loss, right? So when the data points are apart, it's very difficult to figure out a correlation, right? It's difficult to figure out a correlation. Like this one is here, this one is here, and this one is here. So it looks like that there doesn't seem to be a correlation, right? So when the instances are far apart or less in every dimension, it's very difficult to come up with some meaningful correlation, right? So higher dimension data sets are very sparse, right? Because let's say here we have a cube, okay, which is, let's say, 1 meter and 1 meter and okay and 1 meter, right? What we want is that on every centimeter we should have 1 point, okay? We should have dot which is on every centimeter, right? We should have dot on every centimeter like this, correct? Similarly here, okay? Let's say we want dot. Oh, I felt that ink is over in this pen. So dot at every centimeter. How many such dots will be there? Anyone? Okay. 1 meter has how many centimeters? 100 centimeters, right? So it'll be 100 to the power 3. This is a cube and we want dot at a distance of 1 centimeter, right? Which is 1 million such dots, correct? So if you don't have, you can see that even for 1 millimeter, 1 centimeter separation, we need 1 million dots, right, in a cube. Had there been, dimension would have been like 10, right? So how many would we require at every centimeter? We'll require these many dots. If we have like 10 dimensions, then it is going to be really huge, right? So higher dimension data sets are at the risk of being very sparse. Most training sets are likely to be really far away from each other. Okay? So, and when most of the training sets are really far away from each other, the new data sets will also, when we give a new test set, is also will be far away from any training instance, right? And therefore, predictions are going to be much less reliable. Predictions are going to be much less reliable. So, more dimensional the training set is, the greater is the risk of overfitting, right? Or you can say that the more dimensional the training set is, the worst are going to be the prediction. All right. All right. So before the break, we were talking about the curse of dimensionality. We talked about the distance between 2 points, right? In case of, or you can just think about for now the distance between the endpoints of a cube, right? In case of a square, the distance is 1.44, that is square root of 2. And in case of a cube, it's going to be cube root, it's going to be square root of 8, right? Square root of how much? I think it's square root of 4. I have to check that. But yeah, as you can see that in case of the as the dimensions increase from 2 to 3, the diagonal also increased. Similarly, if there is a hypercube, the diagonal also increases really huge, and the volume is really high, and therefore the distance between any 2 point also increases. Now, so higher dimensional data sets are at the risk of being very sparse. Okay. Most training sets are likely to be far away from each other. Is everybody agreeing with these 2 points? Yes? Is it making sense? Okay. So, right, here we are trying to demonstrate that here it looks like it's densely packed, right? But it looks like there's quite a few instances, but if you take a look at each dimension, you'll find that their data is sparse, right? So, and when the data is sparse, the model doesn't come out to be very good, right? Because no matter how great is the model, what happens is that even when we are using, say, a very simple model or very, say, like a recall based model, whereby we're comparing a new instance with existing one and so on, even then we'll never be able to get the great prediction. So new instance is going to be far away from the instances on which we did the training, and therefore the predictions are going to be much more unreliable, right? When the instances are more different than they're similar, right, or they are far apart than they are nearer, then the predictions are not going to be great. Hence, the more dimensions the training set has, the greater would be the risk of overfitting. The greater will be the risk overfitting, all right, because we'll be just trying to memorize the data and we'll be trying to recall based on that. And even then, the outcome is going to be really bad. Outcome is not going to be that great. So the idea is to reduce the number of dimensions. So what we do is, one of the thoughts that come to mind is that, okay, we need these many dimensions, but let's increase the instances. Let's get more and more instances if we have so many dimensions. But reducing the dimension is a better option than increasing the training size. I'll show you why. Okay, though though in most cases that's the option. That the option is to just get more and more data, more and more records, more and more readings, more and more observations, and more instances, right? But if the dimensions are too many, you will require far more number of instances, right? Because as you grow the dimension, right, the growing the dimension has an exponential relationship with the number of instances, right? The area of a circle or number of points required in a rectangle or a square is, right, a square if a is the length, right? A square, in case of cube, it is a cube. In case of four-dimensional structure, it will be a to the power 4, and so on and so forth. Therefore, the number of data points that are required have a exponential relationship with the number of dimensions. Okay, meaning as the dimensions grow, the need for having more instances would also grow, and that would be exponential growth required, right? For example, a data set with 100 features will need more more training sets than atoms in observable universe to have the instances on an average of 0.1 distance from each other, right? So hence we reduce the dimensions. All right. So basically, if you have number of data points really huge, then the number, sorry, if the number of features or number of features are say 100, and we want the data points to be within say 0.1 distance of each other, right? In that case, you will require more instances than atoms in the universe. Okay, I hope this is clear to all, that dimensions, though that looks like a great idea all the time, that people come up with all the ideas that let's put that as also the criteria, but that also increases the demand or the need for number of instances, and that demand or need is exponential to the number of dimensions. All right, so a number of times when we have so many features and we don't have, like, we can't really have that many instances, right? It becomes imperative to reduce the number of dimensions. All right, so the dimensions are not a great thing. That's what the point we're trying to say, that even though dimensions give us better results, if you have more features about something, we know more things about something, then our outcomes are better, right? We have more properties, attributes, but at the same time, in order to train the system, in order to have a better outcome, we also would require more instances. While the common sense says that either if we have more features or more information about someone, we would not require more observations, right? Like, for example, if we have more detailed resume of somebody talking about all characteristics of a person, all possible characteristics of a person, the more characteristics we have in the resume, in order to build a model which can predict a person's behavior, we would require more and more observations of more different people, right? The more characteristics we have in resume of somebody, right? If we are taking up more criteria to measure someone's behavior, right? In that case, we'll require more and more instances. So generally, when the dimensions are too huge, it's better to reduce them, right? There are two approaches to dimensionality reduction. First of them is projection. Second one is manifold learning. Okay, so we'll talk about projection first, and then we'll talk about manifold learning. Most real-world problems do not have training instances spread across all the dimensions. This is a good news, that many of the real-life data sets don't have instances in all dimensions. Many features are almost constant in some of the dimensions, meaning those dimensions or those features have no correlation at all, and while the others are very heavily correlated. Let's take a look at this one. That here, this data set is like this, right? This. So here you can see that across this particular plane, the values are hardly varying, right? Across this particular tilted plane in 3D, the values are hardly varying, right? And therefore, do you think we can drop one of the features? Yes. So, okay. So question is, how many features are there in above graph? How many features would you like to keep? 2 or 3? That's right. So 2 are sufficient. Okay. Let me try one more diagram if I can. I can draw it for you. That if we had, let's say, 3D like this. Okay. If we had a 3D like this. Okay. And imagine that there was 3 data points in this space, like this, right? Okay. So can this be expressed as a straight line? Can this be expressed as a single dimension? If we had this kind of a line, right? Let's say X, Y, Z, and let's say the data points we had was 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, like that. Okay. So do you think we can come up with a data set with a single column? We can, right? Because this line is in like this, right? It's in this particular dimension. Okay. So if we come up, we basically translate it in single dimension, we don't require 2 columns. The one is sufficient. Correct? Similarly here, what we have is this, across this particular plane, right? The data sets are going to be, we basically need two features, though of course there are 3 features in this, x1, x2, x3, right? So yes, I'm going to ignore that question. Okay. Now in this, how many features, which of the feature here is almost fixed across all instances, x1, x2, and x3? X3 there, right? Thank you, Prashant. All right. So most of the training instances actually lie much lower dimension space, refer to this diagram. Okay. So a 3D space could be translated to 2D. Okay. So not all instances are on the second dimensional subspace. If we project all the instances perpendicular to on the subspace, we get a new 2D set. So if we come up with this cleverly, if we come up with this kind of a plane, across which the values are not varying too much, okay, across which you can see that here the data is almost fixed across this plane, right? It's not varying. Okay, so if we can come up with this plane, we can drop one dimension and we'll have only 2 dimensions, this dimension and this dimension. Correct? We don't require 3 dimensions. So if we come up with new set of dimensions, like this and this in this case, then we don't require 3 dimensions, right? So what's happening here is that we have taken this plane, which is cutting across this data, and such that the projections of this is the value that we'll keep, and we'll drop the other slight variance here, right? Because it's almost like similar data, same across all. So as you've seen in the linear algebra, a vector v can be projected into another vector u by doing the dot product, or a vector v could be projected onto a plane by doing the dot product. And this is how we do. So if you want to find out that what is the shadow of this one here, right, with respect to this, so what we'll do is we do the projection of v on in terms of u. Okay, projection of v on u is the dot product of u and v, u dot v, divided by mod of u multiplied by u. U is the direction. Okay, so for the graph below, which of these are true? Quickly, just to do a quiz. V is orthogonal to u, v is projected into u, and u is projected into v. V, right? Okay. Like we project a vector into another vector, we can project a vector onto a plane using a dot product. If we project all the instances perpendicularly on the subspace, we get a new 2D dataset with these features. Okay, I hope you got the idea. This and this. Okay, if you come up with this plane, and take each of the dataset, each of the instance, and do a dot product with that, we will get this, right? I hope everybody got the idea till now. So to convert that data set into two-dimensional, all we need to do is figure out a plane on which we can do the projection, right? All right. So this example has been demonstrated in the notebook. We will show you later. And basically, we can reduce it to 2 dimensions using PCA. You can also open the notebook and try it out right away. Okay, let me also open the notebook. Close it, we don't need it. And now going ahead, where is the dimensionality reduction? Not the copy, but this one. Okay. So this is the part we talked about. Okay. Just let's not go through the code. This is just for plotting. We'll go through this very soon. Okay, so this is it. All right. So a question is projection always good? Can we do the projections all the time? But can the projection be the only solution, right? Not really, not really. So imagine the data set in the form of a Swiss roll. It's a very common data set and has been used over and over to discuss the dimensionality problems. So this data set is called Swiss roll data set, right? And In this data set, if you try to do projection, you would not get great answers, right? So let's take this one. What if we project the training set into x1 and x2, right? If you try to do the projection squashes the different layers, and hence classification is difficult. Okay, so if we have x1, x2 like this, and you try to squash it like this, meaning project it, you get this kind of data, right? Which is really hard to classify. If you think about SVM, think about all kinds of ways, it's not possible to classify it. Instead, what if we opened the Swiss roll? Okay, very good point, Robert. Robert's question is, can we reduce our features by looking at correlation metrics in pandas and then removing features with high correlation? Generally, we drop the features with low correlation. Okay, the one that doesn't have a correlation with outcome. Okay, so yes, that is one quick way of seeing that, okay, looks like this particular column has no relation with the output. We can try to remove those. Okay, yes. Very good point, Robert. So yes, we can. And all right, so moving ahead. But that technique does not always give great results, because sometimes, even though one particular feature is, we are dropping it, but still that one has some correlation. So we are dropping some amount of information. We want to minimize that loss. Okay, so other than looking at the correlation, that is definitely one measure. Second way is to look at dimensionality using these two strategies. Okay, so sometimes projections may not work, and in this case we have to unfold it. So there are algorithms which we'll talk about that basically unfold a data set. Exactly for this reason. So if you see a data set or realize the data set is in the form of Swiss roll, you can unfold it using the mathematical technique. So projection doesn't seem to work in case of Swiss roll or similar data set. Okay, in that case, we'll have to do the unfolding. Okay, the above limitation of projection can be demoed in the following step: visualizing the Swiss roll, projecting the Swiss roll. We have done it already. Okay, in this case, we require manifold learning. So Swiss roll is an example 2D manifold, where 2D manifold is a 2D shape that can be bent and twisted in the higher dimension space, right? Meaning it's a bad sheet, okay? It's essentially a bad sheet which has been rolled over, okay? Or you can think of it like it was we have made a roll out of like two-dimensional thing. So 2D manifold is essentially a 2D shape that can be bent and twisted in higher dimension space, right? A D-dimension space is part of n dimension space, so where d is less than n, meaning like the way 2D became 3D when we rolled it, right? Like when we make the rollout of a paper is basically converting 2D into 3D, right? Similarly, we can take d-dimension space and roll it or convert it into n number of space where n is more than d, right? So for Swiss roll, the d is how much and n is how much. So we convert a d into n, right? Or d, or you can simply say that d-dimensional space is a part of n-dimensional space, okay? And so in case of Swiss roll, how much is d and n? Yes, that's right. So d is 2 and n is 3, correct? So many dimensionality reduction algorithms work by modeling the manifold on which the training sets lie. This is called manifold learning. So what we do in case of manifold learning is that we take this data set and try to unfold it. Okay, so we'll learn that particular algorithm also. So for this Swiss roll, we can model the 2D plane, which is rolled into a Swiss roll, and hence it's occupying a 3D space. So manifold learning relies on the manifold assumption that most real-world high-dimensional datasets lie close to a much lower dimensional manifold. This has been observed empirically. So it has been empirically observed, meaning people have seen it. It's like saying that since we have seen it, so you have to believe it. And it has been seen mostly that most of the data sets have the manifold behavior. Like take a case of drawing, right? Like case of MNIST, good, that's the example. Okay, so MNIST data set, if you see, in case of, let's say, 5, right? 5 is basically a straight line folded into this, correct? Similarly, 7 is basically 2 lines, right? And similar is the case probably with 8. Okay, so basically in MNIST dataset where images of digits have similarity, most of the images have been made of connected lines. All the images are white, and most of the images are mostly centered. So a randomly generated image would have much larger degree of freedom as compared to images of the digits, right? Because if you think about it, the total number of shapes that are possible with 784 pixels is very, very high. With 784 pixels, we can draw the entire of the world, right? In 2 dimension, we can using these 784 pixels, we can actually draw entire world. But if you take a look at our alphabets, there are only 9, right? And so MNIST itself is basically just the digits are itself like connected lines. All the borders are white and more or less centered. Okay, so a randomly generated image in case of MNIST would have far larger degree, and hence the constraint in MNIST images tend to squeeze the dataset into lower dimensional manifold. Okay, so you can always think of the digits also created out of like manifold. They were straight line, but we folded them to make the characters. Okay, so manifold learning is accompanied by another assumption that going to a lower dimensional space will make our life easier. Okay, say for example, if we unfold this one, it'll be easy to just classify the data by the way of drawing a straight line. Had it been like 3D data, it'll be very hard to cut it, right? With a plane, we can't cut it with a plane. Therefore, this is far more easier. So going to a lower dimensional space generally makes the task at hand simpler. Okay, but not always it does. Like for example, it doesn't make the task at hand simpler, because if you are trying to cut it from here, okay, or let's say that there was a manifold like this, right, in which from this plane all the things on the right hand side are different colored, and all the things that are on this left hand side are different colored. These are squares and these are triangles, and when you unfold it, you get a shape like this, right? It's fairly complex. Even for SVM, it's going to be really complex to come up with something. Okay, so the previous 2 cases can be demonstrated in these steps using a 3D Swiss roll and so on. Okay, so summary is so far that dimensionality reduction, there are 2 approaches, projection and manifold. Okay, Reducing the dimensions gives us better visualization, faster training, may not always lead to a better or simpler solution, valid both for projection and manifold learning. Not always, but mostly it gives. Okay. There is, whenever we are dropping a dimension, there's always loss, right? And so we should always try the original data set before going for dimensionality reduction. Okay, you should know what kind of loss you're making. All right. So we talked about two approaches. One is projection and other is manifold. In projection, we come up with a plane on which we project the data. In case of manifold learning, what we do is we unfold a rolled thing into a lower dimension. So the most popular dimensionality reduction out there is PCA. All we need to do is identify the hyperplane that lies closest to the data and project the data onto the hyperplane. Okay, so we need to come up with a hyperplane that lies closest to the data and projects the data into the hyperplane. Question is, how do we select the best hyperplane? So everybody would like to do this, right? That let's get the best plane, which basically can we can project our data onto, and still we lose very small amount of information, and so on. Right? Question is that how to come up with such a plane? How to come up with such a plane? Okay, how to come up with such a plane that we basically retain the maximum amount of information even after doing the projection. Okay, all right. So how do we, here I'll basically do a little deviation. Okay, the question that we are discussing here is that, imagine, so this needs to be converted into, right, this. So right, so question is that we need to convert our data from this. Okay, question is how? Can somebody give me a good approach? Do we do this in our day-to-day life? No? Yes, that's right, Robert. All right. So Robert says that we do this in our day-to-day life when we take the picture. Anybody else wants to add something? What are the things that we do in day-to-day life when we convert 3D objects into 2D objects? Anybody? Yes. When we try to convert 3D into 2D? Shade, yes. Okay. And Gonzalo, that's the most common thing that we do every day. Okay. Every moment, that's what we do. Think about what it means by 2D and what it means by 3D. Every object we see is 3D, while things like shadow, things like a photo, things like the projection on eyesight, on the back of eye, is all 2D. We have two eyes, that makes us see 3D because both eyes have a slight bit of different orientation, different distance from the object. Then using that, we superimpose the two images and look at the distance. That's how we get the idea of depth. But individual eye, the way it does the projection is actually 2D. right? So we do it every moment. We convert the 3D into 2D, right? By looking at things, the projection that is formed on eye is 2D. Taking photos and selfies is again converting 3D into 2D. Now, my question is, let's say there's a group of people, right? There's a group of people who are standing. Think of these as group of people. Now, from which side, which way will you take the photo? There's a group of people and you don't want to lose information. From which side will you take the photo, right? From the front, from the side, from the top? From which side? Not in this case, let's say there is another group of people, right? Can right? So there's this group of people, let's say this, right? We the side that will show, yes, that will cover all of them and should have maximum information. If we took the photo from this side, on the right side or the left side, we lose most of them, right? If we take the photo from the top, we'll only see their hairs and we'll lose the other information. The maximum variant amongst people is mostly the face. Face has so many information that we don't want to lose, right? Therefore, we take the photo from the side where there is a maximum information. There is a maximum variation in the information of this, information of this, information of this, and how much it is varying. Right? So basically, we take the photo from the direction where we can see everybody. Now, this is a good example. When you have so many people, taking the photo from the front, straight front, will be impossible. So you go to the angle from which you can see the photo. So you move the camera in order to reach the point where you can get the photo, right? And the same applies to the dimensionality reduction, that we basically keep on changing the camera, or we come up with the angle where we can cover maximum people, right? So we take our camera, go to the top and look at, okay, we are able to see most information like this, while when we are taking a look from this side, looks like there's not much covered here. There's not much of a variation, and that's what is happening here, right? So we took the photo of this data and we got this, right? So all we need to do is we need to change our x-axis, y-axis definition, and we have to come up with the axis that preserves the maximum amount of variation or variance. What is variance? Variance is that square of standard deviation, meaning how far each data point is away from the mean. So what we do is we sum up all the differences from the mean of everything, and that's what becomes variance. The more is the variance in our dimension, the more information we'll be covering, right? In case all the data set is same, all the data is same, in that case, the variance will be 0, correct? All right. So we are computing the means of all the overall data set in that particular dimension. And then once we compute the mean, then we compute the distances of each one from the mean, and then we compute the variance. Is that a question, Robert? Okay. So in each instance, overall, let's say we take a particular dimension. Okay. we take a particular dimension and we compute the center point of the data, or by doing the mean of all the values, right? And then we see that how far each of the values are from the center. Okay, so lose less information than other projections. So what is that angle? What is that axis on which we'll lose another projection, another information? Okay, so like this. So if we have this data, imagine that we have this data. If we look at this data from here, we get maximum coverage. If we get the data, look at this data from, say, C1, from this side. There's something wrong in this. Okay, C2 means like we are looking at this data from here. C1 means it's a normal one. Okay. So when we select C2, select say C1 as our dimension, this is our C1 dimension, right? This is our C1 dimension. So we get this information, this much, this is how, right? When we select the C3, this is our C3, this is the kind of data we get. If we select this, okay, select this dimension, meaning we are standing here, looking at the camera like here, meaning we are selecting this as our dimension. Sorry, when we are selecting this dimension of the data, meaning we are standing here, our data is here. Here, this is where we are placing our camera. So C2 is like this. So which of the best axis to select to preserve maximum variance? Should we keep this axis? Should we keep this axis? Or should we keep this axis? Yes? If you were allowed to choose only one axis, which axis will you keep? C1, that's right. So yes, we will keep C1. So we want to keep maximum variance as compared to the other axes. We want to keep the axis that gives us max variance. Okay, so I hope everybody got the idea. So even though the PCA looks like a really complex algorithm, but the idea is extremely simple. Okay, so we go to a direction from which we get the maximum variance. Okay, we pick up an axis across which the data is varying more. And then once we have done that, we pick the second axis, which is orthogonal to this one and is giving the second maximum variance. Okay. So the previous case can be demonstrated in these steps, that we generate a random 2D dataset. A question from Deepak is, variance considers the mean of distances of real points from the projected plane? No. So first of all, we project the data in that plane. That in that plane or in that axis, we compute the mean, and then we compute the variance. Okay. So like, for example, here, this one, right? So here you can see this one. Yeah. So another way to say the axis that minimizes the mean squared distances between the original data set and its projection onto that axis. Okay. So that is another way to say that whichever is having the minimum error, let's say okay. So that one is the one. Okay, so here, okay, so what we are going to do is that we are having, let's say, this data set. We're looking at it from this angle. What we do is we compute the mean. So mean as in, this is, let's say, the mean value along this direction. Then we basically compute what is the standard deviation. This one has got highest deviation. This one has got highest deviation. And since we're going to sum up the square it and sum up the deviation, in that case, this will have a higher variation, right? This one will have lower, this one will have lower. Okay. No, original is not. Yeah, this is the original. This is the original, and we are projecting it into 3 dimensions. C1, C2, and C3. This is a 2-dimensional one, and we are converting it into 1 dimension. Okay, this is a 2-dimensional, converting it to 1 dimension. All right. All right. So how do we select the best plane to project the data set into? And how do we do exactly is, in case of PCA, we first of all, we identify the axis that accounts to the largest amount of variance in the training set. Okay, the axis across which the data has got the maximum variance. Okay, even in the existing columns X, Y, and Z, if either of these columns we have got maximum variance, that means that column is far more important than the others. But in case of PCA, what we do is we try to identify first axis across which we have got maximum variance. Okay, that's the new axis to keep. Now, what we do is then we provide us, then this algorithm gives us the second axis, which is going to be orthogonal to the first one, right? There can be many orthogonal axes to one axis, right? There can be many y-axes, okay, given an x-axis. Is this correct? Can there be many orthogonal axes to one particular axis? There can be, right? So imagine that we choose, let's say, okay, let's say we are choosing this as one of the axes, and second axis could be like this, which is perpendicular to this, right? Which is perpendicular to this. This could be another axis, and if you rotate it a little bit, this one could be another. This one could be another. If you look at this one, all of them will have 90 degree. Okay, basically we are rotating it in this plane, like out of my laptop. Okay, out of my laptop. There could be like many more dimensions which are orthogonal to the first one. So first one we choose based on the axis that is giving us maximum variance. Then we pick the second one. Okay, we pick the second axis. Okay, or you can say that, let me reiterate the first one, that what you're doing is you're choosing a direction from which the values of individual people is well spread out, right? Let's say we're taking the camera to the front, we are computing the distance from the center, how far are they, and on both the sides, and then we're considering that. Okay, and then provide the second axis which is orthogonal to the first one that accounts for the largest, and so on. We keep on doing that over and over again. So after we have figured out the second axis, then we figure out third axis, and so on. Important part is that we should have orthogonal data set. We should have orthogonal data set. Now, this is a little difficult concept to grasp. So though it looks really simple that the dimensions need to be orthogonal, but why do features need to be orthogonal? Okay, why do features need to be orthogonal? Meaning that, let's say if we are choosing this direction, we should choose some other, right? Okay, I'll just tell you what it means. Okay, I'll just show you what it means. How do the when they take the photo of a criminal, they have a criminal, they generally take the photo from two sides, right? One from the front and side photo, right? Something like this. That if we are taking a photo, when we're taking photo from the front, we also take the side photo. Okay, so that gives us the complete coverage. All right. Okay. Oh, criminal. What do you say that? I think something like this. Mugshot, they call it. Yeah. All right. So you took the camera. All right. Here we are just taking one person into account. So consider that we are talking about the individual features. So let's say we took the camera, we took the photo from the front, then we took the photo from the side. That covers the entire information, right? But first one has to be the first axis has to be the axis of maximum variance, and the second one has to be orthogonal to the first one. Perpendicular, orthogonal means like vertical to the first one, and is going to cover more and more information. All right, so that's the idea. So the second axis has to be orthogonal to the first one so that we get the better picture, we get the complete picture. All right, and we continue this way until third and fourth and so on. Okay, so the unit vector that identifies the ith axis is called ith principal component. The first axis that you come up with is called first principal component, second axis is called second principal component, and third one is third principal component. All these C1, C2, C3, all of these are orthogonal to each other. Okay, the other way of looking at the way we should always have the features should be orthogonal to each other in ideal scenario, right? Why orthogonal? The influence of one should not be combined in another. That is the ideal scenario. That's what we would like to do, that when we are taking photos are orthogonal to each other, so that we don't have influence of first on another, because that's a repeated information. If we are just taking the photo with a different, like tiny 10-degree difference of angle, we would end up with duplicate photos, correct? There won't be anything much. So the features, right? At the end of day, we will have one feature, second feature, and third feature, and so on. So these characteristics have to be, I mean, when we the information, the principal component that we choose need to be orthogonal, such that the information is not duplicate. Okay, such that we can't really derive the second column from the first column. Okay, such that we can't really derive the second column from the first column. That's what is the principal component. That's why we want to have them orthogonal. All right, now question is, how do we find the principal component? That there's a technique under the hood called singular value decomposition. Singular value decomposition is a technique, is basically based on eigenvalue calculation. I'm not going to go into that. If you want to understand how it works, you can take a look at SVD. It divides the training set into the dot product of three matrices: U, sigma, and transpose. Okay, so a transpose of V, right? Transpose of V contains the principal components. These contain the principal components. So this singular value decomposition breaks down our data set into dot product of three things: U, sigma, and transpose. Transpose V contains this VT contains the principal components, the unit vectors, and so on. So this is how it looks like. So this will be my principal component 1, second, and third, and so on. So VT will be in a matrix where each column is representing the principal components. So SVD can be implemented in scikit-learn using the code below. You can just use np.linearalgebra.svd and provide the x-centered, and you will get the principal components C1 and C2. So how many principal components are we printing here in above question? That's right. Great. So basically what we are doing is here, we are first of all centering our data, right? We are finding, okay, and right, we are moving the center to the mean, right? That's why we are subtracting it from the mean, and then we are basically using this particular mechanism. And okay, so let's take a look at our, this we have already talked about. Okay, so this we've already talked about. Okay, so here it is. We did centered, and then we said, yeah. So this is where we are centering it, and then what we're doing is we are picking two axes, and we are extracting these components. Now, after we have extracted these components, we can project the data and plot it. Okay, afterwards we can do the projection and then plot it. All right, the same thing can be easily done. Okay, all right, going back here, right? We're talking about X here. Which one is the X? We are generating some data probably here. This is our X, right? So there are two axes. One is the column, other is the row. Okay, or let's say we define say data equals 1, 2, and 3 and 4, right? So this is our data, and we are saying data dot mean, okay, axis equals 0. What will happen in this case? What will you get? Yes? I'm trying to answer Robert's question. Okay, so we have the average of this, So axis equals 0 means we are computing the average across the row, right? If we want to do the average across the columns, this is how it looks like. No, actually, let me just, I'm sorry. Here, this is wrong. So what we are doing, axis 0 means average across this plus this by 2 is this plus this by 2 is this. Okay, let me just put it as something like 5 and 10. So this is going to be 5 plus 10 as this, right? Half of that is 7.5. 3 and 1 is 4 by 2, that is 2, right? So across the rows and across the columns. Okay, this one is basically across the column 1 plus 5. Okay, I hope you got the idea. So first of all, we are centering the data set across the rows. We are computing the mean on 0th column, and we are computing the mean across the rows. All right. Once we have computed the principal component, we can just do the projection using the dot product, and we will get the new data set. All right, that's what we get, and then we can continue. And we can pick up how many accesses we want. So initial couple of principal components we can just pick, and we can leave rest. All right. We will continue from here in the next session. Bye-bye. Have a good day.